Good afternoon, class. In today's video, what I wanted to do was to talk about sound. So first, it would be good to define what sound is, and then we can get into more of the different ways that sound manifests itself when traveling through its various mediums, or media, I should say. So sound is defined as a vibration that travels through a medium. That can be solid, liquid, or gas, and it enters your ears, and your brain interprets it as a signal, that's what makes sound, at least for us humans. Because it can travel through solids, liquids, and gases, we need to define the speed of sound, or we need to talk about how sound travels by talking about its speed and how it travels through different mediums to get to where it needs to go. So when we talk about the speed of sound, we'll start with gas, then we'll go to liquids, then solids. So generally air, water, and some kind of solid, take your pick. So in dry air, you've got two basic equations, and the thing about dry air is that there are two different there's a very important mechanism involved, which is temperature. So, and the reason for that is because at low temperatures, the air particles are much more closely packed in together. When it's higher temperature, they're much more spread out. So that's why when it comes to the two equations that govern how sound propagates through air, in particular, temperature is actually really important. This is not as important in solids and liquids, mostly because in solids, if it gets too hot, the solid will melt and turn into a liquid, and at which point this speed of sound, the liquid speed of sound, becomes much more pronounced and apparent compared to the solid one. But in air, everything is very much spread apart and diffuse. So you might have several different equations that would govern this. And of course, it also depends on things like the density of air, the air pressure that comes in, those things come into play. However, to simplify things, we're going to stick with just temperature as our main differential between in terms of how to figure out what type of speed of sound is going to be present given a certain situation. Okay, so in dry air, the velocity is 331 plus 0.6 times T sub c. T sub c stands for temperature in Celsius. That's meters per second. These are for low temperature. Those are low temperature situations. Low temperature meaning around freezing, or STP kind of temperatures, like 0 degrees Celsius. When you get to higher temperatures, like room temperature, for example, then you've got a little bit of a different story, because that's what the high temperature equation would need to come in. That one would be more like, whatever room temperature is at, like 70 degrees Fahrenheit, which is so many degrees Celsius, that would be considered high temperature. So in this case, it would be 331 times the square root of 1 plus the T sub c over 273. That would just get you the approximation in more absolute terms. The nice thing about this high temperature one is it actually does, within a few decimal places, approximate this equation here for low temperatures. It's just that for low temperatures, it's much easier to use this equation as a way to think about it. Okay, so now let's go into the liquid phase. What is the speed of sound in liquids? And that's going to be the square root of beta over rho meters per second. And of course, what is beta? Beta is it's a Greek letter beta, and it refers to the bulk modulus of an object. And every object, by the way, has this. Every liquid and solid has a bulk modulus and a Young's modulus. Both of these are very important. They determine how much things can be compressed and how much things can be stretched. So for the bulk modulus, it talks about squeezing or compressing a volume, and the Young's modulus is how much it can stretch and maybe possibly even shear a little bit or rotate. That's the case before permanent changes occur. So that's for liquids, and then for solids, it's going to be the square root of the Young's modulus divided by the the density. So, and of course, where do you get all of these numbers? Where do you get bulk modulus? Where do you get Young's modulus? Those you would have to look up, or if they're on the test, they would be provided for you. So don't worry about those. Those numbers will be given. I don't expect any of you to have those things memorized, especially because they're actually they're not numbers that we generally deal with in our everyday lives. So with that, that concludes how to go over the speed of sound in different mediums. One thing I note before we end, in general, however, if you're especially if we're talking about like liquids like water and solids, there is a comparison between air, water, and other solids. Of course, it's not always true because every solid is different. Every Young's modulus is different. But in air, you would get a certain speed of sound about the air temperature that we're used to. It's about 340 meters per second, maybe a little bit higher than that, maybe like 343 meters per second. However, in water, with the bulk modulus, it's about 5 times better. So if you've ever heard that number where sound travels about 5 times better in water, that's actually true. In fact, you might have even heard that sound travels 10 times better through solids, and that is also true in general. Okay, not every material will conduct sound as well as other materials. You know, it depends on what solid we're talking about, but in general, solids are about 10 times better at transmitting sound than air. So an experiment, if you ever want to try this, and I would be very careful of doing this because I know that some of you are going to try this, so I might as well say it so that you at least have heard it and can take necessary precautions. But if you've ever listened to a solid, like if you ever put your ear to a door and knock on it, it's actually really, really loud. Even though if you knocked on it the same without your ear on the door, it's actually quite soft comparatively. And that is exactly because the sound traveling into your ears is coming directly from the solid instead of being produced in the air and reaching your ears in the air. One other note in terms of this difference, because there's a solid and a liquid and gas, and there's a difference between those, that actually explains why you don't like the sound of your voice whenever you hear a recording of it. Because whenever you make a recording of your voice, the machine, like this camera, picks up the voice that I'm projecting through from my vocal cords through the air, and those vibrations in the air are what the camera is picking up. However, my ears, which also pick up the sound coming out of my mouth and vibrating the air, they're going to my ears as well. However, it is also traveling directly from my vocal cords through, it's vibrating both my bloodstream and the bones in my jaw over here. So it's actually vibrating solids and liquids before it's reaching my ears as well. So what I hear as my voice is actually the combination of the sound that comes from my mouth, and then all of the sound that travels through my from my vocal cords all the way to my ears as well. So keep that in mind. That's why your voice actually does sound quite different compared to what you would hear it as on any kind of recording device. So think food for thought on there. So that concludes how to deal with sound. Good luck in your studies, and may the force be with you.